Hi, my name is Barry Olney from In-Circuit Design. This is a quick demonstration of the new iCD Termination Planner, which is part of the Stackup Planner software. High-speed design is all about impedance. For perfect transfer of energy and to benefit from the highest possible bandwidth, the impedance of the driver must equal the impedance of the transmission line. Unfortunately, driver impedances are all over the place. They can range from like 12 ohms to 80 ohms. So the idea is that we need to match that driver to the transmission line so that we perfectly transfer the energy over. And you can see here this is simulated in hyperlinks where we have a unterminated transmission line, and you can see the red waveform there has a lot of ringing, and this ringing obviously creates signal integrity issues and crosstalk problems, and also creates electromagnetic radiation. So to solve all those problems, what we need to do is terminate the transmission line. Two basic ways of terminating transmission line. There's parallel termination, which is generally done at the load, and these days in the latest high-speed devices like DDR memory devices, on-die termination is actually built into the chip itself on the input pin. So here we have, for instance, a memory device, and it has pull-ups and pull-downs. Now you can imagine some of these pull-ups and pull-downs are only 20 ohms. And so if we're pulling up from our transmission line to VDD 20 ohms or pulling down to ground, that draws a lot of current. So obviously if you're hanging a lot of these devices in parallel, well, then it creates quite a problem with simultaneous switching noise, because you're exasperating the current that's drawn. The one advantage of on-die termination is that it opens the eye diagram. So you can see on the right there, the eye is wide open when you have the on-die terminations turned on, because it pulls the waveform up and down vertically and creates this open eye. So it's good to have, but if you have a long data bus, for instance, you still may require series termination. Now, series termination, if we looked at the basic lumped element sort of network, you can see we have a driver here which has a series terminator. The driver also has a source impedance and a voltage driver source. That goes into a series terminator and into the, say, 50 ohm transmission line, and then into the high input impedance load. Now, this is a basic voltage divider. So our source impedance and series terminator basically have to equal 50 ohms, which is the impedance of the transmission line in this case. So half the voltage is launched in the transmission line. When it gets to the load at the receiver end, because it's a high input impedance, half of it's reflected straight back, so we get a nice full voltage swing waveform. And that's a simplistic approach. But if you're looking at fast rise time design, then you really need to look at a distributed system whereby you take into account the parasitic effects of the series inductance of the termination resistor, also the inductance of the transmission line, capacitance of the transmission line, and also the capacitance of the receiver. And of course, the more receivers you put onto that transmission line, say if you have 3 or 4 receivers, the transmission line all driving 3 or 4 loads, then that capacitance of the component of the load is all put in parallel, which tends to roll off the signal and decrease the rise time, which is exactly what a series terminator will do. So if we put more loads onto the transmission line, then we need less series termination, basically. IBIS models are good in that they don't give away any proprietary information. They let you know what the input and output requirements are of the device, but they don't deal with any of the internal operation whatsoever. So vendors are quite happy to give these models away or produce these models for people to use for signal integrity. Now, there's some sort of unusual terms they use for the models, and one of them is stub series termination logic, SSTL, which is quite common these days in DDR memory devices. Here I've got an example, or a few examples. SSTL_3 is actually 3.3 volt operation. A 2 is a 2.5 volt, 1.8 is 1.8 volts, and so on. So we have all these different models which can be used for just your standard SD RAM or your DDR4, for instance, and also low power devices. For high speed transceiver logic, this is mainly serial logic, differential serial logic, and it's for operation beyond 180 megahertz, and this has 4 classes, and there can be unterminated, series terminated, asymmetrical parallel termination, which is end termination, or double parallel termination, which is termination at both the input and the load. You can see here we have low voltage CMOS and HSTL and SSTL, as I mentioned, low voltage TTL, low voltage differential signals, all that sort of thing, and there's also differential HSTL and SSTL models there as well. They're a bit confusing, but you sort of get used to them after a while, and some of the vendors do explain to some extent what the models mean. So if we look at the first example here, an SSTL15_OT50_LR_25 model refers to a 1.5 volt DDR3 model, and it's got a 50 ohm on die termination. The I/O is either the left or the right banks in the device, and it has a 2.5 volt voltage controlled oscillator. The second example here is a low voltage CMOS. It's 1.8 volts, it has a fast slew rate, and the I/O is either on the left or right banks again, and it's a 2.5 volt voltage controlled oscillator. Alright, so let's look at the iCD Stackup Planner. First of all, I'll just change over to a DDR3 Stackup, which I've done before, and we'll select a strip line layer in the center here somewhere, and then I'll turn on the Termination Planner. Now, as you can see, the Termination Planner has first of all, the trace impedance, which is taken here from the characteristic impedance of the signal layer that we clicked on to start with, and it has a trace length. Now, obviously the trace length has something to do with the loading, because the longer the trace, the more inductance and the more parasitic capacitance you'll have on that transmission line. And also the number of loads, as I mentioned before, tends to roll off the rising edge and acts as a low pass filter. So that also has an effect on the series termination. So let's look first of all at a typical Xilinx Vertex 7 FPGA, and we'll click on the component, and here we have all the signals within the FPGA, and there's over 1,000 pins here, so there's quite a few of them, and you can see what I was talking about before, the HSTTL differential logic here for the high-speed serial links, mobile DDR for instance, and this again is a differential. We have the differential SSTL with different voltage ranges, and here we have a single-ended HSTL models. So basically what we can do is pick out the model we want, and then we click on the driver model, and this gives us the series termination required for that model on this transmission line of this particular length. Now, as I mentioned, if we increase the number of loads, well, obviously we don't need as much series terminations because it rolls off the rise time of that signal. And also if we increase the length, also we require more series termination to stop it ringing so much. So I'll just put this back to 2 inches again. Here we've got our low voltage CMOS, and like this is a 24 milliamp drive current of 1.8 volts. So in that case, using that model on this transmission line, you would need a 27.24 ohm series terminator. If, for instance, you had an 8 milliamp drive, you would only require a 19 ohm termination. We can go down here, and we've got mini low voltage differential signals, and we've got PCI 33 megahertz drivers. We've got the 1.3 volt, which would be used for low power DDR3 or DDR4 device, 1.5, which is typically used for DDR3, 1.8, which is DDR2, and so on and so on. So there's all these models you can choose from. So if you know what you're doing, you can select the exact model from the Vertex 7, for instance, or any other model. Now, quite often you don't have the processor or FPGA model, simply because if you're developing the FPGA yourself, then you need to generate the model using the development tools. In that case, what you can do is use a micro memory model instead of the processor model, simply because the data bus is bidirectional. When it's writing, it drives from the processor into the memory, and when it's reading back from the memory, it goes back into the processor. So being the same technology, you can use the driver on either end, basically. So let's select a DQ0 data signal, and you can see here that we have 3 different speeds. We have 1066, 1600 and 2133 megabits per second, which is 1 gigahertz basically, the fastest speed for this particular device. And we also have 34 ohm source impedance, or a 40 ohm source impedance. And what you can do is program the FPGA to give you that particular source impedance. Now, for a 34 ohm source impedance on this particular transmission line, this trace impedance of a length of 2 inches and 1 load, we need a series terminator of 18.37 ohms. Now, DDR3 and 4 should really work on a 40 ohm transmission line. So if we change it to 40, then the series termination is 7.55 ohms. If we program the FPGA to have a source impedance of 40 ohms, which is more like the transmission line, then we only need a 2 ohm resistor, which is pretty close, so I wouldn't worry about that at all. And of course, if you increase the length of the transmission line, so we make it 5 inches, then the series terminator will increase. And also, if we add more loads to the transmission line, the series terminator will decrease. So it's all a matter of looking at the parasitic effects of the transmission line. Most terminators will, be between, maybe 12 and 33 ohms. So you can go through here and you can click on all the signals and inputs. The receivers are disabled because we're just looking at the drivers in this case. But if you don't have the models and you still need to find out an estimate of what in termination impedance you need, you can use the generic models. And we'll just load the IC generic model library here. And you can see what I've done here is got all the basic models. So if you're using a straight DDR SD RAM device on a 50 ohm transmission line, you'll need a 30.28 ohm. DDR2, 21 ohms, DDR3, 11 ohms, and like I said, if you drop this to 40, which DDR3 should work at, then you'll only need a 2 ohm or basically no series terminator. DDR4, we also have the low power DDR3 as well here. And we also have things like display, GPIOs, HDMI video, and we've got our standard HSTL and low voltage CMOS, all that sort of stuff, low voltage TTL, and some simple NAND flash devices. So as soon as you click on it, it works out the termination required, and you can add the number of loads that you may need on this transmission line. Unfortunately, with mainstream PCB layout software, we really don't know, or we have no idea what the driver impedance is, let alone the capability to match the driver to the transmission line. And so this new feature, the iCD Termination Planner in the Stackup Planner software, allows you to match high-speed drivers to transmission lines. Thank you very much.